Hi everyone, welcome to the third video for Module 10, in which we've been talking about non-independent error terms and how to deal with this statistical dependence in our different study designs. In the video today, we're going to be talking about crossed designs, where we have repeated measurements, where, for instance, we might have subjects who are measured across 3 different conditions, right? And each subject is measured in each condition. And because each level of one factor is represented at least once at each level of another factor, we have what we would refer to as a crossed design rather than a nested design. So in the video today, we'll be working on the example from the textbook, in which we had participants rating their anxiety under conditions in which an experimenter was absent or an experimenter was present, right, while they completed this task. So each participant, right, each YHI, completes the task under both experimenter absent conditions and experimenter present conditions. So because each person is represented at each condition, that means that the factor of participant is crossed with the factor of condition. Right, and we have to understand then how to deal with the statistical dependence in our data, because if we simply analyze these data as independent bits of information, what we would find out is that the residuals from one participant are more alike than they are different, and we would have a positive non-independence in our data. So similar to what we had to do with the nested example, we're going to create an ANOVA table in which we partition the variance into different categories. And we have to remove the statistical dependence between people, right? Control for the fact that observations from one people are more alike than they are different. And once we remove that variation, then we can actually do a fair test of the effect of the effect of condition. Then we can do a fair test of the effect of condition in order to fairly say what happens to anxiety when the experimenter is absent versus when the experimenter is present. So here is the ANOVA table from the textbook, right? And follow along with our subscripts, right? Where H is equal to condition and I is equal to participant. We're going to then need each of these additional bits of information about what the mean of each condition is, what the grand mean is, right? And what each participant's average is, in order to fill in this table. And what we're going to want to do is remove the variation between subjects, right? We want to remove the variation due to which person you are, so that we can more fairly evaluate the variation due to which condition you are in. So we're going to walk through how to actually fill in this table based on our different model predictions and our different pieces of information. And the important thing to realize is we don't actually have independent pieces of information here. They are statistically related because some people have higher scores, some people have lower scores, and regardless of which condition you're in, higher people tend to stay high, lower people tend to stay low. So first, how do we calculate the total sum of squared errors? This hopefully feels a little bit old hat by this time, right? But we're going to take each observation and we're going to subtract off the mean of means. So for each observation, each y sub hi, right, we subtract off the mean of means. We'd square all those deviations and then add all of those deviations together, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 times 2, right, is 16 total observations. So we're going to have 16 minus 1 for this parameter. So we have 15 degrees of freedom with respect to calculating the total sum of squared errors. Next, we can calculate the total variation within subjects, right? So our scores are crossed by condition, but they are grouped within subject. So we could say, all right, then if we want to test the effect of condition, we have to take the 2 scores from each subject, subtract off the average for that subject. That will tell us how much variation there is within a person. So we take each YHI, right, each score in each condition, subtract off that subject's mean, then we're going to and square it. Then we're going to take the next score for that person in that condition, subtract off that subject's mean, and square it. Then we do the same thing for the next participant. We take the score minus the mean squared, the score minus the mean squared, and thus for each participant we are going to have 2 error terms, 2 residuals, right, that tell us were they above their mean or below their mean in a given condition. We'll square all those error terms and add them together, and what we're going to end up with then is sum of squared errors equal to 5 and a degrees of freedom equal to 8 in this situation. Next, we're going to calculate the total between subjects variation, right? So for the between subjects variation, this tells us how much subjects vary relative to each other, right? And the total sum of squared errors in this case is based on taking the mean that we observed for each person minus the grand mean, right, which is an estimate for the true mean in the population. So there's one parameter being estimated here. So we have our 8 observations minus the one parameter that's being estimated. We have 7 degrees of freedom. And if we were to take each of these scores minus the mean of means and square it, we'd end up with 18 sum of squared errors for the total between subjects variation. So one thing we should notice here is that people tend to differ more from each other than they do between the conditions, right? We have a lot of between participant variability here, and people tend to be quite different. So our between subjects variation is relatively big, whereas our within subjects variation is relatively small. Within that within subjects variation, then, we need to decide how much of it is explained by the effective condition and how much of it is sort of left over, right? How much is unexplained variance? So the first thing that we're going to calculate is that unexplained variance. So this is akin to the sum of squared errors of the residuals, right, or the SSEA that we've calculated in previous examples. The formula looks a bit different because we're dealing with this crossed factor, right? But what we're trying to do is remove the variation due to which subject you are, right, to then say how much unexplained variation is there. So what we would formally be doing can be written in 2 different ways, but the first way to look at it is for each score, we're going to have that score minus the subject's mean, and then we're also going to remove the average difference, right, in that condition. So we're going to have each score, the average then of each score minus the mean for each subject, but we're going to average those across conditions. So the sort of more simple way to write this, the more straightforward way to write this would be to say that we're going to take the difference between the score and the mean for each person minus the average difference in that condition. So that tells us, was this person different from the average difference in that condition, right? So this would be this score minus this score minus the average of all the differences between our participants. And again, that's going to give us a residual because that's going to tell us how far away is that person from the average difference in that condition. Once we have that calculation, right, we could actually calculate the SSR, right, the sum of squared errors reduced by the effective condition, just by subtracting the unexplained variance away from the total variance, right? 5 minus 2.75 is equal to 2.25. But that's not very informative. And what we actually want to then see is, okay, how can we calculate the sum of squared errors reduced for the effective condition? And again, we can write this formula in 2 different ways. In one instance, we can write it as, what does the model predict for a difference minus that person's score, minus what is the average of the averages for each person's score minus their mean. So that's not super intuitive, but the way we can think about that a little more simply is we will have an average difference in each condition, right? So for each person in each condition, our model predicts the average difference away from the subject's mean. And we'll subtract away from that the mean of means for differences. So we take the average difference overall, right, minus the average difference in that condition. And if we squared those deviations and added them together, that's going to give us the total sum of squared errors within explained by condition. And then we will have a sum of squared errors reduced and a sum of squared errors of the residuals that we've had in the past that has appropriately removed the variation due to which subject you were, right? So we've accounted for the within subject correlation, the fact that scores from the same subject tend to be more similar. And by removing that variation from our data, we can now fairly look at the effective condition and actually say, does having the experimenter present or absent have an influence on your anxiety? And then by calculating a mean squared error of the reduced and a mean squared error of the residuals here, we could calculate an F observed now that the between subjects variation has been removed.